In our earlier discussion of pulleys, we talked about the reaction forces that could be developed at the pulley bearing. To identify support reactions generally, we need to first identify the so-called degrees of freedom, meaning translations and rotations, that are prevented or impeded by the supports. For every degree of freedom prevented or impeded, a support reaction exists. At this relatively early stage of particle equilibrium, there aren't that many possibilities, but we'll discuss these four. First is the pin support. As the schematic indicates, the pin can be thought of as a shaft mounted between opposing flanges, which are in turn mounted rigidly to a supporting surface. The pin is free to rotate about its axis, but it cannot be pulled through the flanges, so its translational degrees of freedom are restrained. This leads us to represent the pin reactions as Rx and Ry, one force component for each translational degree of freedom prevented. It should be noted that there are a few special situations involving pin supports where reactions or forces communicated between pins are simpler than what is shown here. In a couple of examples so far, we've looked at links, which are pin supported at two ends and connected usually to something else. So here's an example of a link, and there's a pin at A and a pin at B. And so using this discussion that we have here, we would normally say, okay, if I'm isolating this section involving this link, I should have an AX and an AY component on this side, and I should have a BX and a BY component on this side. And yet, if you think about some of the problems we've looked at so far, we've reduced this to something much simpler than that. We've either had the same member in compression or in tension. So instead of having four unknowns, we have just one, either a tension, or if the arrows are going the other way, it would be a compression. So how is this possible? Well, it will turn out in Chapter 6, we're going to look at a special case involving an element like this, and we will be able to show that if we have a slender element that's pin supported at both ends and has no intermediate force between the pins A and B, so for instance, if we can neglect the weight of that member, then that is reducible to this member that we have here, where there's a single force communicated and the line of action of the force goes through the pin connections. This is going to be called a two-force member, and identifying elements as having this property allows us to greatly simplify problems. So for now, we're going to say pin supports generally require two reaction components, Rx and Ry. But in the special case of this link, pin supported at both ends with no load between the ends, it's reducible to this much simpler two-force member. The second situation we're going to look at is the so-called rough surface. Here the term rough is used to indicate the presence of friction at the surface. This is qualitatively different from the pin because translation in X isn't prevented. It is impeded or resisted. Resistance is less restrictive than prevention, but still requires an Rx reaction component. Friction differs from the pin in other important ways. The particle must be pressed into the surface, so the Ry component must turn out to be positive, as shown in the reaction column. Also, friction is always dissipative. It always acts to oppose actual or impending motion. So if the other forces acting on the particle are tending to push it towards the right, Rx must act to the left, and if the other forces are acting to push it towards the left, Rx must act to the right. We will have much more to say about friction as we get to the end of the class. For now, we'll say that even though there are X and Y reaction force components in both cases, the nature of the reactions provided by the pin are significantly different from those provided by a frictional surface. It is also the case that we will run across problems with elements mounted on or in frictionless surfaces. In practice, we may use the term frictionless surface to indicate a well-lubricated interface between interacting components. It may not be that friction is completely absent, but rather is so small that it can be neglected. The two cases shown here differ only in that the slider or collar is restrained from the inside. We can't pull the collar through the rod, while the pin is constrained from the outside. It is constrained to move along the track internal to its guide. In these cases, there is a single reaction component normal to the bar or guide. The absence of a component tangent to the bar or guide indicates no resistance to motion along the guide. In this final example, the driving mechanism for a steam locomotive is shown. Piston A is acted upon by steam pressure P, which drives piston rod AB. Plate B, called the crosshead, slides without friction on guide DE and is connected to the wheel by bar BC. We're to idealize plate B as a particle and draw its free body diagram and find the force in bar BC and the reaction between B and guide DE. So once again, there's a lot in this figure competing for our attention, but the problem statement specifically directs us to the crosshead plate B to draw the free body diagram. So we're going to focus on that. The pressure in the cylinder to the left of A will provide a force that has to be reacted by member AB. So we're going to know the direction of the force exerted on the crosshead by member AB. It will be in compression, and we'll be able to calculate that value. We note that member BC is pin connected at both ends. We're going to assume that the load that's transmitted by BC is large compared to any weight that it has, and so because it's pin connected at both ends and we can ignore any intermediate forces, this will turn out to be a two-force member, and so the force that's transmitted by BC will be along its geometry. Finally, we're told that plate B slides without friction on guide DE, so we will replace the guide with a force normal to DE, or if we use a conventional XY coordinate system, a force in the Y direction. We're going to have three forces acting on the crosshead. The first force will be the compressive force from the piston. We're going to be able to calculate that. I'm going to write that as FAB. That's shown pushing into the joint at B because member AB will be in compression. It will turn out that member BC will have to counteract that, so I will also show member BC as being in compression. And making a 20-degree angle with the horizontal. And finally, because the guide is frictionless, it will have a reaction force between the crosshead plate and the guide that's purely normal, and that will also be in compression in order to counteract the vertical component of BC. So I'll draw that as FDE. We know FAB because we know the pressure and surface area on the other side of the piston. This turns out to be FAB equals the pressure times the area of the piston head, which is pi over 4 times the diameter of that piston squared. At 100 pounds per square inch, acting on a piston with diameter 8 inches, we get a net force of a little over 5,000 pounds. Static equilibrium in the x direction requires FAB minus FBC cosine 20 is equal to 0, and FBC sine 20 minus FDE is equal to 0. From the first equation, FBC is FAB over cosine 20, and that number turns out to be equal to 5349 pounds. From the second equation, FDE is FBC sine 20, and using our value of FBC, we find this is 1830 pounds. The fact that these numbers turn out to be positive indicates that we guessed the directions correctly. Remember, BC is in compression, and the crosshead engages guide DE from below. Perhaps a more important question is whether we can really use the equations of static equilibrium in this kind of a problem. The motion of a piston, connecting rod, crank-driven system is inherently cyclic, which means the motions of the components in the drive system are far more complicated than just motion in a straight line at constant speed. Perhaps if the locomotive is just starting to move, the accelerations of its components can be deemed sufficiently small to justify the use of static equilibrium equations. Otherwise, we must incorporate principles from rigid body dynamics, but that's a story for another time. We'll try a few additional problems now, then take a short break from particle equilibrium to discuss other mechanical components before returning again to particle equilibrium in 3 dimensions.